My name's Nathan Van Zaney, and welcome to the channel. If you're new here, Catching Steam is just a way for me to share my resources to other educators. And this video is for anyone who teaches chemical and physical changes. So what I have here is 8 different stations that students interact chemicals at, make observations, and determine if it was a chemical or physical change. So in this video, I'm going to walk you through the general setup on how I do this in the classroom. Then I'm going to go through each station, tell you how to prepare the chemicals, and then give you an explanation on why it was either a chemical or physical change. What students are going to see when they go to each station are 2 sets of chemicals, a container to interact them in, along with a set of directions. Now for the liquid chemicals, I recommend these 4-ounce bottles with a built-in eyedropper. Having this built-in pipette makes it really easy for students for measuring, and it also makes it really simple for cleanup because students just put on the lid and then you have the pipettes and the chemicals all ready to go. If for the stations that have 2 liquids, I recommend using these 5 milliliter test tubes. They're plastic with a built-in lid, and them only being 5 milliliters makes it so students only really need 2 milliliters of each chemical. They put the lid on, then they shake it up, and that provides plenty for them to be able to make their observation while hardly using anything here. That means you can easily go through all your classes in one day without having to refill these. One thing that helps simplify this for me is to divide this activity into 2 days. So the first day, I'll have students do stations 1 through 4. The next day, it's 5 through 8. You're probably thinking 4 stations is not enough for my whole class, and you'd be right. So what I did is I doubled each station. So there's 2 sets for station 1, 2 sets for station 2, 3, and 4. So I still have 8 stations out. It's just there's a copy of each one, if that makes sense. And then so that way, I only have to prepare 4 different sets of chemicals before my class period. Then the next day, I can use my prep period to prepare for the next set of 4. Station number 1 involves phenolphthalein and a base. Now this is actually the 3rd video I've made using these chemicals. One of them is another really good chemistry activity, while another video explains how viruses spread in a population. So these are good chemicals to have in your classroom for a multitude of different activities. But how you set it up for station number 1 is I just get a little bit of phenolphthalein. Doesn't take hardly anything. You put that in the container. Now this powder does not dissolve in water. So you need a little bit of rubbing alcohol to get this powder dissolved. And then you're going to stir it around a little bit. And once this is dissolved, you can then add water and you have your solution made. Now I'm going to make a recommendation. I recommend you get either distilled water or reverse osmosis, like cheap bottled water, because a lot of tap water is actually slightly alkaline and can already make this reaction happen. This is just going to be bottled water. And because I'm making 2 stations at the same time, and each of these bottles is a little over 100 milliliters, I'm going to make about 200 and 225 milliliters. There. Now I'm going to take this and pour it into each of these phenolphthalein containers. Now this may be obvious, but don't fill them all the way to the brim because you still need to put these pipettes in there. But there's one, and then I'm going to fill up the second one. And now that's the first half of station 1. So again, this is labeled phenolphthalein, and I put 1A on there, and I have 2 of those containers. Now for the ammonia, I just have to have alkaline water here. So your tap water may actually work if you just fill this up with the tap water, but just to make sure that everyone here is able to do it, I'm just going to use some regular water. Again, this is just cheap reverse osmosis water. You can also use distilled water. Pour that in there. Okay, so this just being water, I have to make sure it's alkaline. Now, it doesn't take very much ammonia to make this work. So what I'm going to do is I'm going to now put 10 milliliters of ammonia in about 100 milliliters of water. So I'm using this pipette. Feel free to use a graduated cylinder, whatever you need. I'm just going to put about 10 milliliters in each container. Now I put the lids back on here, and station 1 is finished. This one is ammonia, and it has 1B, so that's going to be at one table, and this is going to be at another table, along with these plastic test tubes, and then a set of directions. And that's it for station 1. So just to show you the reaction itself, and then give you an explanation, I have 2 milliliters of each solution. So I'm going to go 1, 2, and like I tell my students, I only want one container open at a time to prevent cross-contamination. And now I'm going to do 2 milliliters of phenolphthalein. 1 and 2. And then on the directions, I have them put the cap on, give it a shake, and you can see that these 2 clear liquids made a bright pink solution. Now this is an example of a chemical change because you observed a color change. So you had 2 colorless liquids and now you have pink. All right, station number 2 is pretty simple to set up. I have food dye and water. I'm not going to set that up for you because you just get some water, I put blue food coloring in it, and then I found the scientific name for blue food coloring and I put that on the label there, and then I labeled it 2B. And then on this one, I put isopropyl alcohol and labeled it 2A. Now, I did not fill this up with isopropyl alcohol. I just put a little bit in there and filled the rest up with water. So I just went like this and then filled the rest up with water. And I did that for both containers. Now, the reason why I like to have this one in here is because a lot of times students think if it's colorful, that it was a color change. So what some students will see when you do this, you'll put 2 milliliters of the isopropyl alcohol, mostly just water, and then they will put 2 milliliters of this blue food coloring in there, and they'll be like, oh wow, it's blue now. It's a color change. Well, in fact, it's obviously not a color change. It was already blue. But this is just to make sure that students don't just think, hey, it was clear, now it's blue, that therefore it's a chemical change. Well, no, you just mix these 2 chemicals. I realize that one may seem simple, but it's a very good one to have in these stations because it does make sure students are making observations beforehand, and it makes sure that just because it is a color, they don't think that a chemical change just happened. It has to change colors. All right, now we're at station 3, which is one that I know all of you have seen before and probably all the students have seen before. It's just baking soda and vinegar, but I have the scientific names on there. I said sodium bicarbonate and acetic acid. These are, again, very simple to set up. Just put vinegar in these ones. And this one is labeled acetic acid 3A, same thing here. And then these are sodium bicarbonate labeled 3B. So now I know these go together and these go together. Now I really like having this one because it's really going to set them up for another one that is a little bit trickier. So in case you haven't seen this before, students are just going to take 1 scoop of sodium bicarbonate, and then I have them put 4 milliliters of acetic acid. So because there's only 1 liquid here, instead of doing 2 and 2, I'm going to do 4 milliliters. So that may mean you may need to fill these up kind of towards the end of the day, but still it's pretty straightforward. There's 1. Now, as I'm doing this, I'm noticing a lot of bubbling. You can feel that it's actually getting cold. So maybe you could use they can use a thermometer and see that it's getting colder. But 2, and then I can start putting more in there. So this one should be pretty straightforward for students, that you had a solid and a liquid, they mixed together and created a gas. And in this case, they're producing CO2. And so this is a chemical change. Now at this point, these have been relatively simple, but I promise they're going to get a little bit more complicated for students. Now station number 4 involves dissolving. For the dry chemical, I'm using dextrose. You can use any artificial sweetener like Splenda, anything you want. The reason why I want to use dextrose is because I have another station that needs dextrose. So rather than getting 2 different chemicals, one for station 4, one for another station, dextrose works for both of them. And for the liquid, I'm using dihydrogen monoxide, also known as water. So you can insert all those little jokes there and tell them how dangerous this chemical is if you want. But how it's going to work for chemical 4B for dextrose, you're going to use 1 scoop. Honestly, you could probably use about half a scoop because it takes about 10 milliliters of water to dissolve 5 cc's of this. But you're just going to put your dry powder in there. And then you're going to take your dihydrogen monoxide. I instructed them to do 10 milliliters with the full scoop. Again, you can do half a scoop, but they'll notice that this is going to start dissolving. And so now the question is dissolving a chemical or physical change? And the answer is it's a physical change. It may look like this chemical is disappearing, becoming another chemical, but that's really not what's happening. These bonds are just breaking down and they're dissolving into the water, but the chemical itself is still there. And if you were to evaporate this water back out, the dextrose would be left behind. Now on, let's say, the baking soda and vinegar, if you were to let that sit out, it's not going to evaporate and then all of a sudden turn back to baking soda, okay, because a chemical change happened there, while this is just a physical change. It's kind of just a mixture. For this one is tough for students because you did see a powder, now you don't. Just make sure you test this one ahead of time. Make sure your directions are in a way where it does completely dissolve that solid. And that's the reason why I like to use like dextrose or Splenda versus sugar, because sugar doesn't really dissolve that well in room temperature water. You need a lot of water and a little bit of sugar, and you honestly kind of need to heat up the water a little bit. So artificial sweetener seems to dissolve a little bit better. First one in day 2 at station 5, I see a lot of educators get this one wrong. It involves expanded polystyrene. Some people call it styrofoam, but it's technically not a foam. I'm not going to get into that too much. And the second chemical is acetone. This is also sold as a fingernail polish remover. There are a couple different kinds of fingernail polish remover, so make sure you get the one that says acetone on it. But I recommend just buying it at a hardware store because it's a lot cheaper this way, I feel like. You were going to put the acetone in these 4-ounce bottles, and this expanded polystyrene, I just break them off into chunks like this and then put them in a container. So for the directions, I instruct students to put 2 pieces of expanded polystyrene in the container, and then you only need about 2 milliliters of acetone. This stuff can kind of smell, so make sure you have your windows or doors open if you can, and then try not to have them use a lot of it because then it just kind of makes your room smell a little bit more. But 2 milliliters seems to be plenty. So I just go 1 and then 2. And then you'll notice it doesn't dissolve. You will notice some bubbling. So you see some bubbles coming off. So you had a solid and a liquid, and you see some bubbles coming off. So you're probably thinking, okay, chemical change. And then you also notice it doesn't dissolve. It kind of turns into a slime. Because if it were to dissolve, we know that's a physical change. But if we now look at this, if I were to take this out, it turns into like this putty looking stuff. So it looks like it's forming a new chemical. And even though it looks like it's a new chemical, and you saw bubbling, this is actually a physical change. This is not a chemical change. It is a physical change. All right, and before you get all mad at me in the comments, let me explain. This expanded polystyrene, how they make it is really cool. So I recommend looking up how this is actually made, but essentially it's inflated plastic. It's plastic with air in it. Now this acetone, all it does is it releases that air that was already stored in the plastic. So you had a mixture of air and plastic, and then the acetone separated them. And separating a mixture is not a chemical change, it's a physical change. Other examples of the same thing would be like Pop Rocks, which have a gas stored in a sugar, or Diet Coke and Mentos. That is also a physical change because it's releasing the gas that was already in the soda. So if you unmix a mixture, so if you take a gas that's in a solid or liquid and you separate them, that is a physical change. Now, just to really hit my point that this is plastic, I'm going to let this acetone evaporate out, and then you'll be able to notice that this turns back into a hard plastic. Now we're at station 6, and we are going to be making oobleck. And this is where you're going to need to kind of play with it to see what the right ratios are for whatever size scoop that you have. For what I did is I used 2 scoops of these 5 cc's. And then typically I use about 4 milliliters of water. Sometimes you need a little bit more depending on what their scoops look like. But now I do 4 milliliters of water. And then on my directions, I have students stir the oobleck. And then at this point, most students know what they're making and they realize what it should be looking like. And I'll admit, this is a station you seem to be running through materials really quickly because they end up wanting to make more and more oobleck. After you start stirring it up, it can almost feel like glue, like a putty when you're moving it really fast. But it's going to look like a liquid. And what I also like to do is when students are done with this, done with their cups, I have extra cups there for the other groups, but I kind of like to take all this and just pour it into one cup and have it at the end. And then I can kind of just be, making observations with students over it because it does feel really weird. And the more that you get, the more you can really feel it. But I don't want all my students to be making a big cup of this oobleck because that's just a huge accident waiting to happen. But you can really still feel the effect with just this small amount. All right. Now, the question is this a chemical or physical change? Now, it does look like a chemical change because it doesn't really act like water. It doesn't act like cornstarch. It acts like a completely new substance. But this is a physical change. Similar to like the dextrose and water, if we were to let the water evaporate out, you'd be left with the cornstarch again. So no new chemical is made. It's just a mixture. So this cornstarch is almost kind of suspended within the liquid. Now, station number 7 is called the methylene blue reaction. Typically involves 2 dry chemicals, liquid called methylene blue, and then water. But rather than students having to mix all 4 of these chemicals in the right proportions, I made it in a way to where there's just 2 solutions and the students still get that same effect. To prepare the first solution, you're going to need a chemical called potassium hydroxide. This stuff is not great for your eyes or skin, so make sure you're wearing safety glasses and gloves. We're going to dilute it quite a bit so it's still relatively safe for students, but still use this with caution. Now, I'm going to use a scale and my beaker. So I'm going to put my beaker on here, I'm going to hit tare, and I'm going to zero it out. Now I'm going to take my spatula and I'm going to add 7 grams of potassium hydroxide into this beaker. Now after that, I'm going to add 250 milliliters of water. So after your potassium hydroxide is dissolved in water, you're just going to simply fill it up in your 2 containers. And half of station 7 is set up. Now for the second half of station 7, we are going to need the dextrose that we used from station 4, along with a chemical called methylene blue. You can buy this online, and there's also a lot of fish stores that have this as well. Now I'm going to add 9 grams of dextrose to this beaker. And it doesn't have to be exact, but get it pretty close to 9 grams. You're then going to add 200 milliliters of water. You need to make sure this is either distilled water or reverse osmosis water. If this water is tap water and that water is slightly alkaline, this reaction is going to start happening inside your container. Because what's happening is this methylene blue wants to react with the dextrose, but it needs to be in an alkaline environment to be able to do that. So that potassium hydroxide is what's going to start this reaction of the methylene blue and the dextrose. So again, I'm going to add 200 milliliters of water and make sure it's properly dissolved. Now this next chemical you're going to need is called methylene blue. Now the amount I'm going to leave up to you. If you want this reaction to happen a little bit faster, only add 1 milliliter. If you want to take a little bit longer, you can add up to 2 milliliters. So for the sake of this video, I'm just going to add 1 milliliter of methylene blue to this solution. Now I'm going to pour it into these containers, and then station 7 is finished. To actually react these two chemicals, you're just going to need 2 milliliters of each solution. So 1, 2 of the potassium hydroxide. And then for the methylene blue and dextrose, I'm going to add 2 milliliters as well. 1 and 2. Now at this point, I'm going to put on the lid and shake it. So what's going to happen nearly every time is students are going to view this as the same thing as station number 2. They see blue food coloring and they see clear liquid, and now they see a lighter blue color. So they're going to think that this is just a physical change because it's a mixture. But some chemical reactions take a while. And in fact, these two right here are the same thing as this. But if you wait about 2 minutes or so, a minute and a half, 2 minutes, this is going to become clear. And the best part is once you take this clear liquid and you shake it again, it goes back to blue. And the reason why I really like this reaction is because there are a lot of teachers that will say, if it's easily reversible, it's a physical change. And this, even though it's easily reversible, this is still a chemical change. In fact, what's happening is these chemicals are reacting with the oxygen. And when they run out of oxygen, it becomes clear. And if you shake it again, it can mix with the oxygen and then it goes back to blue. So what you're seeing is the presence of oxygen in this solution. Now, if you want to speed this up, you can make the potassium hydroxide slightly more alkaline. Now, I'd recommend not adding more potassium hydroxide because I don't want this to become dangerous for students, but you can use tap water instead of reverse osmosis water, and that could make your reaction go by a little bit quicker. You can also use less methylene blue, and then that will also make this chemical reaction go a little bit faster. But as you can see, this is now back to clear. And if I were to take any of these again and shake it up, it goes back to blue. So for this station especially, I like to have students leave these test tubes off to the side. And then when students are doing their reaction and they look over to the previous students, their solution is clear, while theirs is still blue. So some students will notice, hey, why is theirs clear and mine blue? And then this is where I start going to those stations and be like, hey, take their test tube and shake it and see what happens. And then they'll notice that it goes back to blue. Now, I will say this station does not have an infinite shelf life. In fact, it's typically after a few days, you might need to recheck it because even though this water isn't alkaline, they slowly may be reacting with each other. But either way, this is a really good reaction to have in these set of stations. So this last station is the vitamin C variant clock reaction. And again, I made it in a way to where there's just 2 solutions that you interact. So to make this first solution, you're gonna need to make some starch water. This part is not that precise. You just need to get some cornstarch, put it in a large beaker, and if you want, you can make some more than you really need and just keep it off to the side in a separate container. So after you get some cornstarch in a container, you're then gonna add some hot water and then stir it up. At this point, this is way too cloudy to use for our different reactions. So what I'm gonna do, let some of that cornstarch settle to the bottom, and then from there, I'm gonna run it through a coffee filter so I get some starch water. Now, while this starch water is settling, I'm gonna go ahead and start the next solution. So what you're gonna need is 25 milliliters of this 10% povidone iodine. So right here, I have a graduated cylinder, and I'm just going to pour this out to 25 milliliters. Now here, I'm going to take about 1 gram of ascorbic acid. The more that you add, the longer this reaction takes. So don't put in too much. But you want to make sure there's enough to where the solution turns clear. So I'm going to take about 1 gram and then add 200 milliliters of water. And again, I recommend having reverse osmosis water. Now you want to make sure this ascorbic acid is dissolved really well in this water. Now this on its own is a pretty cool chemical reaction, but I promise the one that we're doing later is a little cooler. So you can see I'm adding this really dark liquid and it's still clear when I add it to this solution. Now at this point, I'm just going to go ahead and stir the solution, and it should be clear when you're finished. Now if you want, this could be your chemical reaction, but the one I'm going to show you is a delayed chemical reaction that my students love. So now that my solution's made, I'm going to go ahead and fill up these bottles, and the first part is finished. This is solution 8A, and now we're going to go ahead and finish up solution 8B. This next part maybe isn't necessary, but it does improve the effect. I want this to be as clear of water as possible. So what I want to do is run this starch solution through some coffee filters in a funnel. Now, if you can tell, there's some starch water settled to the bottom, and this top part doesn't look near as cloudy. So what I'm going to do is I'm just going to pour that clearer section in and kind of leave this darker section behind. Now again, for this, feel free to make as much as you want because this starch water stores just fine. But for the sake of this video, I only need 100 milliliters. Now that I have 100 milliliters of relatively clear starch water, I'm gonna go ahead and finish up this last solution. And to do that, I'm just gonna add 100 milliliters of starch water and then 100 milliliters of 3% hydrogen peroxide. Hydrogen peroxide itself does not have a very good shelf life, so I recommend just picking up a new bottle each year just to make sure that it's not going to mess with this reaction. And the last solution is finished, so I'm just going to go ahead and add these to the containers and show you the reaction. Now, just like before, they're going to use 2 milliliters of each solution. You're going to put the lid on and give it a shake. At first, it's going to look like nothing's going to happen, but this is a delayed reaction, and it will eventually turn a really dark color similar to this povidone iodine, maybe not quite that dark. So again, this is one of those things that, and there it goes. So this is slowly turning a dark color. Now, if you want to make this reaction go a little bit faster, you can use more iodine, more hydrogen peroxide. You can increase the temperature of the solution, or you can decrease the amount of vitamin C. But either way, this is a delayed chemical reaction that 2 clear liquids turn a very dark color. So I think it's kind of important for students to realize that not all reactions happen right away. Some of them take time. Some of them are reversible, or they can keep reacting with different chemicals back and forth. Now, overall, I hope that you found these stations useful. One big tip I'm going to give you, though, is don't just tell students the answer on if it's a chemical or physical change. Have them make some discussions, do a little bit of research, or have some further investigations. Don't just have them come up with their decision and then tell them if they're right or wrong, because that's really not what science is about. Now, between these 8 stations, you have plenty of opportunities for students to experience being a scientist. And that's what I really love about this activity. Now, if you have your own reactions that you think would be great in a setup like this, put them in the comments because I'm always looking for ways to improve. Now, if you have any other questions, feel free to let me know. But hopefully you found this video helpful, and thank you for watching.